Welcome everyone to this distinguished lecture in a series of talks that we've given in this Access Center of KTH. We are very happy to have Professor Mostafa Ammar from Georgia Institute of Technology visiting us today. And Mostafa has visited us once before in 2011, and we're happy to have you back.
Thank you.
And it should be sooner until next visit. Mostafa is Regents Professor at Georgia Tech at the School of Computer Science, where he has been working since 1985. And his current research is mostly on cloud computing, mobile cloud computing, and network virtualization. He has a very illustrious career, and I will not eat up all his speaking time by going through his CV. So he's been editor-in-chief of transactional networking at the ACM and IEEE Journal. He's a fellow of the IEEE and also a fellow at ACM. And we're very happy to have you here. Please.
Thank you, Gunnar, and thank you for inviting me second time, like you said, to speak here. I'm glad that every 7 years I have something different to speak about, so that's always good. I hope you get to chance to look at this. This is from a poem by William Cullen Bryant, mostly a 19th century poet. Basically, it says that we should not complain when things are changing. In fact, we should complain when things don't change. It will be a miserable existence, really, if things never change. And this talk is really about change. And I've entitled it, you can't really see the top, but that's okay, the Time-Traveling Computer Networking Researcher. And subtitled something about the consolidation and fragmentation of the internet. So we will go through the meaning of all of this. So we'll start with this time-traveling networking researcher. And you know, I'm a fan of the Back to the Future movies, and this time traveler left in 1985. It's actually around the time I made my PhD. And shows up last week on June 4th. And it's actually an interesting thing to know, to try to think about what happens to this person. People have been in networking for a long time, even 10, 15 years. We see things changing very slowly, and so it's very hard to see the big difference that has been made in networking and in networking research in particular. So I'm going to do 1985 to 2018. In 85, there is really hard to know what the network looked like, but one picture of the network is this one that I'm showing you. This is really one of the backbone networks that was built around by NSF, the National Science Foundation in the US, and it has 6 nodes basically. And in 2018, it's really very hard to visualize the network, but this is the best visualization. This is from what's called the Skitter project at University of California, San Diego. And what they've done here is built a graph, and you can look up their webpage to understand exactly how they did it. But basically, it's a graph of the interconnected networks that make up the internet. Every node in this graph, and there are 70,000 of them, that's why it's very hard to see, 70,000 nodes. Every node is essentially actually a network with many routers. So if you multiply this by 10, you will get 700,000 routers. So the network moved from 6 to 700,000. That's 5 orders of magnitude, quite significant increase. If you look at applications, of course, applications have been quite different. I remember the early days of networking was file transfer was the main application. Today, of course, we're doing social networking, we're doing video streaming, we're doing a number of applications that really in the early days of networking people couldn't even imagine. Perhaps the big thing today is content distribution. Content distribution is the application that is run on the network. What is interesting, I think, historically, is that content distribution, in my mind, is more fundamental than the internet. So a lot of people think that the internet enabled content distribution, but in my mind, content distribution is just a demand that we have as users of content, of digital content, and would have happened either way. And people This is a forgotten kind of system in '85. These are the kinds of systems that we were using for digital content distribution. A lot of the things that you see there are things that we do today on the internet, but this was not the internet. These were television screens, so the graphics are so bad. But also there are things that, weather forecasts, radio station, travel guides, everything you can think of. This is, remember, this is 1985. They even had things like, if you look in this one, in the top one, what you will see is something says telesoftware. This is in 1985 where you could download software from the network onto this was computer sold by the BBC in England. And so everything that we're doing today, they were doing in '85, just the technology was different. And had we not had the internet come up, something else would have done. We would have been doing the same things we're doing today, but on a different kind of infrastructure. Of course, today the internet is ubiquitous, and we run a lot of applications on it. Video streaming being, clearly the biggest dominant bandwidth user today. Let me, I think, also speak to the research approach that this traveler would see. So when they get in the car and they've been doing networking research, this is how we did it in '85. We were really engineers at heart, and we were thinking what we are designing is an artifact. And as you design everything, basically there's a cycle you go through. You design it, you build it, and then you sit back and enjoy it. If you think about cars, if you think about airplanes, if you think about anything that we use today, it's being designed, built, and then used for a long time. And so we thought that we were going to be able to do this with networks, and we were going to be able to come up with some fundamental rules about how to design them. And so there was papers that looked like this. This is by one of the co-authors is Bob Gallagher, who people, if you don't know, is one of the big names in information, very early days of information theory, later became a networking researcher. And this is the kind of work that he was doing, in 1985 on analyzing routing and flow control in networks. Very fundamental work, and I think the thinking was this was going to lead us into how to build networks right away. Today, if you go and you skip everything in between and you look at what we do today, it's actually nothing like this. In fact, it's almost like waking up to a nightmare if you think about it. Basically, the cycle never ends, and the way we think of networks today, they're so complex, they are beyond any real fundamental rules for designing. The only way you can prove them is you have some ideas and you build it and you measure it and you experience it with the understanding that all your experience is going to lead you to the next version. It's never going to end. So you basically go in cycles over and over again. I show you an example here of the QUIC protocol. I'll talk some more about it from Google, but basically this is an example of the last iteration, for example, of how we actually do network transport today. There's also something else about networking research that, again, this time traveler will see. So as they go in the car before they do the time travel, this is what it looks like to them. So they last attended ACM SIGCOMM in 1985, and as people that don't know, ACM SIGCOMM conference is today the most prestigious kind of conference. In '85, it was not. Actually, the idea of a prestigious conference was not even on us. We didn't know what it meant to say something is a prestigious conference. So SIGCOMM was just a gathering where people got together and talked about research. There was nothing really very unique about it. But you look at the publications there are 22 papers. The average authors per paper was 1.9. There were many, many, many. Probably half the papers had a single author papers. The maximum number of authors per paper was 3. Okay, and people were doing work that looked like this. Very, you look at the titles; they're very descriptive of what it is, but also very generic because this topic of window selection and flow control and all that is very big. But the idea was we're going to solve it in one paper. Fast forward to 2017, 2018 sitcom hasn't happened, but I have the statistics from 2017. So I had more papers. Sitcom has gone up and down in the number of papers, but in 2017 had 36 papers. The average authors per paper is 6.3. A clear difference. I've done these statistics for a number of years. This is the first time I've seen a 2-author paper. Before that, the minimum was 3. Never seen a 2-author, so just ruined my statistics. But this paper had this conference had 1 paper with 2 authors. The maximum number of authors was 24. There was 1 paper with 24 authors. So today, if you're just by yourself, researcher sitting in your lab writing papers, forget it. You are not going to get a paper into SIGCOMM. Of course, today SIGCOMM is the prestigious conference. You publish there, and the world opens to you. The other thing that you notice here is the titles now become totally uninformative. If you look at the beginning of this title, taking the edge off with espresso. I don't understand what you're doing. What is the research? I have no idea what it is. So you always have to have, first of all, you have to have the name, because there's so much going on. If you don't call it something, people will forget it. So you have to call it something. So this is the espresso system, okay? But then even they try to explain what they are doing, scale. And by the way, I don't really mean to be critical, because I'm just as guilty. I do the same thing now with my papers, right? So this is not critical of these people. But this is the community as a whole is becoming like this. So now you read the thing, it doesn't even tell you what it is, right? Scale, reliability, and programmability for global internet peering. I mean, this is such a big thing. Before we knew this, they were doing window selection. So they were selecting the window, right? Now I actually have no idea what they're doing. After I read this long title, it has something to do with coffee or something. I don't know. But anyway. But what you see is a distinct change. Of course, this happens slowly, but you see it in these 2 time instants. You see basically that we have changed completely. As a bit of an aside here, you want to think of poor people like me, and there are a couple of people in this room that got trained in '85 and now have to live in this other world, and you cannot sleep, or people will things will take over. Anyway, this is for entertainment value only. I show you a picture of me in 1985. But also I was doing the same thing. You'll see, I mean, I had this is probably the last single author paper I wrote. But I was doing work on my own, as a young assistant professor. Very mathematical. More recently, though, I've obviously look different, but also I haven't done the 24 author paper yet, but I have had 6, 7 author papers with collaborators in multiple institutions, and work has a cute title and things like that. But the community has changed, and now we don't think too much about what used to be. Okay, so this is the snapshot. What I want to take you through now is the process in between. So my talk really is not about this. It's about what happened in between and whether we can learn anything for people that didn't time travel, that didn't jump. What did we see along the way, and how can we interpret that into the future? But a few caveats. First of all, I'm not really talking about internet history or networking history. There's a lot of good publications on that. And then I'm not listing my own research, so you saw probably the only thing I'll talk about in terms of my own research, those 2 papers. The other thing is I want to also be careful, because I may sound critical, but first of all, I have hindsight. I'm looking back, so that's easy to see things. But also, I'm just as guilty as the next person. I've lived through this, and I do the same things that I'm sometimes critical of. So I don't really mean to do that. The last thing I should say is I've been giving this talk for a while, and then last summer I decided I wanted to sit down and put some of this on paper with appropriate citations and make it much more formal. And so there's a paper that came up in the SIGCOMM Computer Communications Review that basically has a little bit more detail and a lot more citations for the stuff I'm talking about today. Okay. So there are 3 parts here. They will go relatively quickly. In the first one, what I want to do is I want to talk to you about how I think networking is really an answer to a need. So you all heard the saying of necessity is the mother of invention, and I think networking is basically the invention that met the necessity. And I'll try to show you what this means in networking, in networking terminology. And then I will discuss two things. One is the past, and one is kind of the present and the future. The first, the past is really what happened in how networking kind of consolidated everything we can think of under this one umbrella we call the internet today. And I'm using some Latin terminology here from the e pluribus unum is the motto of the United States, basically from many one. Okay, so that's the, and then I had to learn Latin to figure out what's the opposite of this, and it's ex uno pluria is the opposite, right? It's from one many, and I think that's what's going on today and into the future. So let's start with the I also want to kind of tell you what to take away so that you watch out for these things as we go through it. So first of all, there is what I'm going to argue is there's a fundamental iterative process that has governed the evolution of networks, and that fundamental process today led us to a single internet that delivers all services. But I want to argue that this is nothing fundamental about this. It's a kind of if you want to think about it, is a local equilibrium that we reached. But we could have hit any other kind of equilibrium over time. And there's nothing really major or significant about the place we're in now. So we can easily leave it and go somewhere else. And this is what I'm going to argue that into the future, we're actually going to leave this local equilibrium into some other point. Where not a single network is going to deliver everything, but we're going to have many networks around that to deliver things. And this is in some sense good news. It's not bad news for networking. It's good news for networking, and I will argue why. Okay, so this is kind of the things you take from there. So the first thing I want to say is the necessity is the mother of invention, and if you want to talk about it in networking, in the networking world, you basically, necessity, if you think about it, is our desire to support services like content distribution. Sometimes though the necessity comes from scale. So and we'll talk about this a little bit. Basically, networking is challenging because of scale. It's not because of what we're doing, but because we're doing it at scale. And if we have to connect two computers, it's relatively easy. The challenge really is how do you connect, a million computers, having them all talk to each other. So that is the challenge. And that's what we are trying to build the network for. So the invention in this case is the infrastructure that delivers these services and handles the scale. So you basically want to say necessity is the mother of invention in networking means service and scale support motivates infrastructure deployment. So taking this one step further and talk about this visually, so you can see this essentially as a flow chart. Basically, we have some service or we have some scale we want to deliver, or both. And for that, we build a network, okay, to deliver that. And networking has seen this kind of behavior many times. The one I'm going to describe in a second is that we build infrastructure to support the service or scale. For example, the early days of internet, there's some argument about why the networking was started. But I believe the consensus is around the fact that the early days of networks were all about remote computer access. So computers were expensive machines. You could only have a few. In any, in the US, there may be 3 or 4 computers, big mainframes. But a lot of people wanted access. So we built this network to provide people access from terminals far away to the computers. And as this network was built to do that, they realized, hey, we're actually doing a lot of emailing around that. And as we decided we want to do email, we built another infrastructure around it. So basically, and every time we decided, well, email is good, but now we're doing file transfer, and now we want to do the web, and then we want to do video streaming, and so on. So every time we realize there's a new service, we go back and change the infrastructure. in this basically continuous cycling. Okay, and you know, you can any point in networking history, you will see these kinds of things develop to deal with new services, but also new scale. And an example of that is, in the old days, there were few computers, so you could actually just have tables that describe all their addresses. Over time, the number of computers increased, so we needed something like the domain name system to handle address resolution. So there are many examples of this. And I'm going to call this the service infrastructure cycle. Let me talk a little bit about scalability, because that is really the main driving force today and into the future. It's the ability to handle a large number of connected entities. So that's what scalability is. In fact, in my class, I joke that basically if I ask them a question and they don't know the answer why we're doing something, doing it this way or that way, if they answer scalability, they have a good chance of being correct. You know, so always, if you look at what the network is doing and why it's doing what it's doing, typically it's the answer is because we want to do it at scale. We want to handle large scale. I also see scale as never ending. Basically, you know, we will continue to have larger and larger scales that we have to deal with. These are the kinds of numbers today. For example, there are 3 billion internet users. Today, people are estimating about 10 billion connected devices, and these numbers will double or quadruple within 2 or 3 years. So that will continue to drive the network evolution. Okay, so this service infrastructure cycle, going back to that, basically continued to operate to give us new and improved infrastructure to handle more services and larger scale. Around 2005, though, people started talking about this. There were papers that were complaining about the inability of the internet architecture to adapt to new pressures and requirements. So meaning that we can think of new requirements and perhaps new scale, but the internet is unable to be changed to handle or to respond to these new requirements. So and people started giving it a name, ossification. Another kind of cute way of saying it is you can't teach an old dog new tricks. So, and the internet basically was getting old. And you will see it being talked about here. So this is one of the papers that where it's saying that there is ossification, which means alterations to the internet architecture that address its fundamental deficiencies or enable new services have been restricted to incremental changes. So we're basically unable to respond. And you know, I have not seen it described this way, but if you want to talk about it in terms of this cycle model, all it means really is this, that the cycle is broken now. And we are stuck in the sense that although the demands continue to be there, we are unable to respond. So this arrow that we had going from the service to the new deployment we're unable to traverse that. However, the cycle is fundamental. So I'm going to argue quickly that, just give you evidence that this cycle is really fundamental, that without it, nothing could have happened. So let me show you this. So I'll start by talking about unicast routing. And unicast routing is basically the ability to deliver data to a specific network address. Very fundamental. Without it, the networks don't work. So very early networks had it, but very early networks were small, so the routing was very simple. As time went by, the network got larger, the routing got more and more complicated. And this is really the best way I can describe what's going on. What you will see is, what you have here is the x-axis is years. On the y-axis is a graph of the number of attached hosts to the internet. This comes from some measurement studies that people have done. This is not my graph. I copied it. There is a link up there from where I got it from. But I will superimpose on this the routing, unicast routing work over the years. You know, even before 1969, there's work you can see, but it says Prosser by Prosser that in 1964 that had very fundamental. If you read those papers, they're a two-part papers. You read these two papers, you'll see everything that actually has ever come later in network routing described there. So all the ideas came out very quickly. The first deployment really was when the internet was very small in 1969. Protocols that were called distance vector routing. If you don't know, that doesn't matter. But basically, what you should realize is this distance vector routing is not a scalable technique. It doesn't work for very large network, but it was fine. The network was very small, very few attached hosts. So it was a suitable thing that we could deploy and use. A few times, so now keep them in mind the cycle. So as you know, this was fine. Now the network grew in scale, so we had to develop new routing. And in came something is called link state routing. And link state routing is allows more scale. So larger networks can be supported with link state routing. And this came in the early 70s. Still, link state routing is only feasible for its larger network, but not very large network. So as the number of networks, the network grew and the number of attached hosts grew, we now needed some other form of hierarchical routing. This should say EGP here. So protocols called a protocol called the Exterior Gateway Protocol was developed to handle even larger networks. But even that was not very good for very large networks. Slowly we had, and this should say BGP down here, we had many iterations of the Border Gateway Protocol, which is also able to handle even larger networks. What you will see quickly is there were 4 versions of BGP that came in about maybe 7 or 8 years. However, since then, there hasn't been many because of ossification. Actually, the timing is interesting because I argued around 2005 the network ossified. What you will see is there is very little real deployment of anything else beyond what we have. We are stuck actually at BGP version 4. And there is no more, even though there are standards and ideas and papers on how to do things like security, for example, for BGP, the deployment has been lagging because of ossification. And it's not a coincidence, you know, that everything after that, you don't really see very much going on. So this is really an example of this cycle in operation. In fact, if you look at the standards, you will see it. You will read the words. So here is what the BGP, remember, this was one of the later standards that was developed after EGP, and you will see specifically what they say. It says it's built on experience gained with EGP. So EGP was deployed, they learned from it, and built BGP. So so this is the cycle basically operating smoothly. It gets stuck, but that's different. That's a different problem, but the cycle really gave us what we have today in internet routing. If you look at multicast, what you will see is a very different things. Very different kind of progression. With multicast, for people that don't know, multicast is basically what I'm doing now. It's the ability to talk once and have many people hear you at the same time. And it's a very fundamental form of communication. We do it actually today when you send group emails. And in fact, the streaming of this video in live form is a form of multicast. What is going on though today is the multicast is happening at the application. Or we think of it as doing it at the application. The network is not supporting it. So the network is sending many streams, one to each user. So in principle, it's scalable, but the way the network deals with it is not. And you know, this is the kind of picture that kind of shows scalability. If you were to send the same thing 3 times without multicast, you will send it like this. If you had multicast, you have data copying in the network, and you're able to send essentially less data over the network to achieve the same objective. So multicast is not widely deployed today. And I will argue the reason is we never really got it to where we ride the cycle, where we actually deploy it, gain experience from it, and then adopt, learn from it and adopt the next version. What happened with multicast, if you again look at the same graph that I showed you earlier, probably the earliest piece of work on multicast is a paper by Dalal and Metcalf in the late 70s that described techniques to do multicast routing. But that was on paper. The first internet proposal, you can't read it here, but it's by Lorenzo Aguilar in 1984 in SIGCOMM, in fact. SIGCOMM 1984 was the first proposal to do multicast on the internet using essentially IP protocol. The problem was, and the details are not important, the problem was it was not scalable. You could not deliver multicast to more than 10 people. So because of the way they were doing it. And people said, this is not scalable, we are not going to deploy it. Okay, we're not going to use it because it cannot handle large networks. But look at when it happened. The network had 1,000 hosts at the time. And rejecting something that goes to cut you by order of magnitude when you only had 1,000 made no sense. But we had no deployment of this and no experience. So no chance really to ride this cycle, to get the next thing. So over the years, what you will see is more ideas. But because we never had any deployment, there was no way to gain any experience from these ideas. Again, this doesn't show here, but this says large groups at the bottom. But basically, for people that know, this is a protocol. It's called DVM-RP that was able to handle the very large groups. It had problems. Again, never really deployed. We only saw it experimentally, and so we never really gained any experience with it. Fast forward, really, a lot of stuff happened. Finally, in around 2005, 2006, we got a protocol called PIM-SSM. Again, the details are not important. That everyone agreed was this is the right kind of model and this is the right way to do multicast. The problem is the timing. By the time we finally agreed on how to do it at scale and all that, it was impossible to actually deploy because the network had ossified. Okay. So this is an example of a sequence of events where we did not ride the cycle. We just worked outside of it, trying to keep thinking, call that an anticipation of the cycle, trying to think far ahead of something we might need, although we don't need today, and waiting for us to have the right thing. By the time we had it, it was too late. If you think about internet, the Unicast routing, the very earliest one, distance vector routing, was not scalable. It is known not to be scalable. And had we waited, we said, OK, we're not going to put Unicast routing in the network, we would not be where we are today. And so it's strange that people insisted here that we wait until something works for these large networks, even though we didn't even have them. So this is an example, and this is my argument why this cycle is really fundamental and was really important to actually have working for the successful evolution of the network. OK. So I basically argued that the success of protocols was when the cycle was followed, and the cycle today, though, is inoperable. Remember that basically because of ossification, the cycle does not operate. But I've argued it's fundamental and it's inoperable. So we will look at this question in a little bit. But first, I want to talk about this thing that we take for granted, that today we have a single global infrastructure that has all services. Okay, and this is my visualization of this. Basically, we have a Swiss Army knife to handle all the tools. If you're really a handyman, and you can't really use this, as you know, to do anything meaningful. But that's essentially what we have today. But there was a time when this wasn't the case, right? So I saw this book in Gunnar's bookshelves, and I have it from 1987. This was the book you studied networking in by Misha Schwartz for a few years. And if you read that book, you will see that he talks about multiple networks. And in fact, this is what we call the internet today, the ARPANET, but it's not, it's just one of several. It was considered a research network. And in fact, when in real life, so other than studying in textbooks, when you went home, you had many networks. I had a network at work that was not connected to my network at home. I used America Online, which you dialed in, and you had all the services that you have today. You can book travel, you can buy groceries, in fact, and so on. But it was not connected to anything. And then when I wanted to build an experiment, I went and got an account on ARPANET and built my experiment. So there were many networks, each had its own use. Today, though, we have a single network. We don't really think about this. And like I argued, this is not an obvious conclusion to where we were, right? It's a local optimum. Clearly, it has some value. But I don't think we appreciate too much that we were led to this point. And we don't really talk about it as a significant milestone in the networking world. There are reasons why it makes sense, right? That those days the main goal was connectivity. I want to connect from one point to every other point, and it makes sense to have a network. We needed scale, and we needed economies of scale. You know, we really were not, we couldn't afford to build a network for everything, right? A separate network for everything, so it made sense. It had though some problems, and one of them was on networking research. It basically stifled innovation. There was a time, there's still some remnants of that, where if you went to a funding agency and said, I have this great idea on how to build a network, they said, forget it, because whatever you're proposing is not deployable on the internet, doesn't matter how good it is. Also, a lot of times early ideas are not scalable, and people were completely rejecting anything that does not work for hundreds of millions of users, okay? And you wouldn't give you a chance to try it on 10 and then figure out how to make it go to 100 and then figure out how to make it 1,000. No, it had right away, the idea had to be provable for 1 million or 100 million people. And you know, I've been the recipient of these kinds of reviews over time, and you know, people adjust. The other problem was, and you know, I can't blame them, because how do you validate your idea? You have a great idea and you actually argue that it works at scale, but how do you prove it? There is no math, there is no simulation that can show you something works at scale except trying it and making it work at scale. So, so people started thinking, well, we can't really put it on the internet, although it was experimental at some point. Now we have all this commerce and real life going on, we can't disrupt it. So there are many, many systems that were developed to actually provide experimental environments to give you the validity or the validation. M-bone for multicast, Q-bone for quality of service, 6-bone for IP version 6. More generic ones, Planet Lab and Genie in the US. Planet Lab has also significant European presence. I would argue none of them really satisfied what people were looking for. Even though you had validated something on Planet Lab, people were still questioning it doesn't work, it only works on Planet Lab. So there was a lot of this and a lot of money spent, especially you know, on Genie, on Planet Lab, that really did not provide what people were looking for. So this is really the impact of this single network on networking research. I will also argue that the single network is what led to ossification. If you think about it, if we continued in this world that Misha Schwartz was showing with many networks, by definition, you couldn't ossify. Basically, even one of the networks might get stuck, but you can build a new network if you want, just add to the repertoire of networks. So the one network is what led to ossification. Without it, by definition, we cannot be ossified. So now the question is this. So I've argued that you need this cycling to have network evolution. I've argued that we are now in this world with one network, but that network is ossified. So basically, maybe we should pack up and go home, because there's nothing we can do. The one network cannot be changed, right? And if it cannot be changed, we can't do anything different or new anymore. So are we done yet? So let's see what's happening. So this is my argument, is that the internet is now fragmenting. Okay, and I'll try, and this is now where I'm getting into the a little bit more speculative kind of direction. Everything I talked about is really happened, but I just added structure to it. Now I'm going to argue that this structure kind of leads to some conclusions, and I'll give you some evidence of early signs of this. So I see us going back now, where we really need some very fancy tools that the Swiss Army knife of one internet is not able to deliver anymore. And you can read the quote, it's tough to make predictions, especially about the future. This is Yogi Berra, is a famous baseball coach in the US. So take it with some of it with a grain of salt, but I'm going out on a limb here and making predictions. Okay, so let's go back to this picture. We said this is fundamental. So, but what's happening is the network demands are not stopping. I mean, if you think about it, we have more scale demands, we have more service demands. Content providers now, there's a lot of money, a lot of interest and a lot of power by content providers. We have a lot of application-specific requirements of latency, and some of them are critical for safety applications. And so what are we going to do? So if you think about it, this is kind of the classic example of what people call the unstoppable force meeting the immovable object. So this is the unstoppable force, is basically the continued change in demands and scale. This is not going to stop. It's just going to keep pressuring on the internet. The internet is ossified. We said it's just not going to move. Okay. So what happens, and what happens, at least this is my prediction, is the network is going to yield. It's going to break from all this pressure on it from services and scale. Okay. So basically the internet is yielding, and what I'm arguing is we're going to see a fragmentation now of the internet, and we're beginning to see signs of that. So let's see what these early signs look like. So the first question I will ask you is Google using the internet? So, you know, of course, I mean, by definition, in some fashion, Google is the internet, right? But let's watch this. So people here, I hope, are familiar with traceroute. If you're not, basically, this is a way to figure out the route from where you are to anywhere in the network. And this is traceroute from my office at Georgia Tech to Google and to google.com, basically. And what you see here is you see a few hops. At the beginning here, you see the IP addresses. This is Georgia Tech. And then at some point around the 74 here, you're actually in Google's network. So basically, going from Georgia Tech to Google, remember this picture with the 70,000 autonomous systems that the internet, basically, I don't see any of this. I see Georgia Tech and I see Google. I'm betting you do the same thing here. You see the same thing. You see KTH, and then you see Google. You don't see anything else outside. So the internet's completely gone, except for these two hops, essentially. One belongs to Google. The other thing is if you use Chrome and you do some incantation here at the top, basically it reveals what protocols Chrome is using. And I have a bunch of things here with Chrome, with Google Maps, Google Scholar, YouTube, and so on. What you will find is Chrome is using this thing called Quick. And Quick replaces HTTP, TCP, and TLS. So basically, the secure connection protocol. So basically what you're seeing is Quick is Google, no TCP, no HTTP, no TLS. There's really very little that is not Google in the network except a few hops at Georgia Tech, right? But not only that, and for a while, although that has gone away, Google was going to replace that. The part that was not Google, they were going to replace it with Google. The only part that was not Google was the few hops at Georgia Tech. This is actually a picture of Atlanta skyline, but the Google Fiber was coming to Atlanta, and so even your ISP was going to be owned by Google. So ISP owned by Google, content provider owned by Google, the transfer protocol is owned by Google. And so what happened to all this internet stuff that we even teach in class? It's gone completely. So this, by the way, Google stepped away from doing Google Fiber networks, so this effect is diminished somewhat. But essentially, Google is not really using the internet, not as we teach it in class. Mostly they're using stuff that is their own stuff. So that's already a fragment. I mean, it's a big one, but it's a fragment of the internet. This is something sitting on the side that is not really the internet as we know it and as we teach it. This is happening more and more, though, because we are shifting. I mean, remember the early days of networking was about connectivity, just getting a bit pipe from you to me. Today, it's not about that. It's more about content delivery. And the content providers are big businesses that have a lot of power. They are very much interested in the relationship with the customer because the customer is subscribing to them, paying them. That's their business, so they care about the quality of experience. They don't like anything between themselves and the customer, so even the little bit of the network that they don't own is a problem to them. And they want to be in total control of the interaction with the customer. This is a very quick tutorial. In the old days, the user was here, connected to its ISP, there was the network, and the content provider was here. Slowly, the content providers decided this was too much, so they would link directly. So you would have the content provider linking directly to the ISP that the user subscribes to. So you get this picture today. Basically, you are sitting here. This is the ISP that you subscribe to at home or at work. And these are the content providers connecting directly to that. There is this thing that's the rest of the internet, but if you look at the amount of traffic that you get or over as a user, a large percentage of it, maybe 80%, would come from these big content providers and not through this big complicated internet. Even more today, these content providers are not happy with this picture because they don't really control this anymore. So increasingly, they're finding ways to get in, putting servers here, have relationships with the ISP. And so the picture actually starts to look something like this. And I'm calling this zero-hop network, essentially, whereas before we had at least the access ISP hop. Now you're directly, within your ISP, you're already talking to the content providers. And so from your perspective here, forget about this rest. This is the very minimal amount of traffic that you would experience. Most of it you see this way. And so you're talking directly to these separate networks that are really not what we think of as a single network delivering all services. We're seeing multiple networks. Through a single interface, but we're seeing multiple networks. Now, there is actually something that is more clear in what you will see around is these, what I call dedicated bypass networks. People have been building these for some time. Whenever the network doesn't provide you what you need, you just go build your separate network. And one of the earliest ones was something called spread networks. This was a dedicated network between New York and Chicago for stock trading because they couldn't afford any more than a few milliseconds. And it gives you 13 milliseconds, basically round trip time from New York to Chicago, and so you can get stock trading. This is probably the earliest example I could find. Over time, there were other things. Sigfox, I don't know if people are familiar with it. That's a European-based company that has coverage. I don't know if it has it in Sweden, but has had it in many European countries. They have their own infrastructure. They ride on the cellular towers, but a total end-to-end solution from Internet of Things devices to servers, no TCP/IP, their own set of protocols. Everything is their own, and quite successful. Again, the reason they built this is because they can handle the large scale of Internet of Things, whereas the current internet is challenged to handle all the additional traffic that would be caused by this. Plus, a lot of the protocols in the internet are too heavyweight for the kinds of things they need for Internet of Things. Another example, this is a startup called Haste that is for gamers. Again, they will provide very quick end-to-end latency for people playing online games using their, the details are not clear here, but if you dig deeper, you'll find they built their own network essentially. It's bought their own set of routers, everything. They pick up your traffic and then send it through their network and to the game servers and back. And so they don't use the internet at all. FirstNet is an example. There were some bad experiences in the US with first responders, people that respond to fires and hurricanes and earthquakes and so on, that because their traffic is going on the internet's either down or they're competing with all the other people making calls and doing all sorts of things on the internet. So they decided, okay, we're going to build our own network that is separate from the internet to handle all the traffic, critical traffic for us. So you'll see a lot of this. Modern networks, if you look at 5G, which is still a little bit up in the air in terms of what it is, you will see people talk about these multiple layers of networks that are doing different things. High bandwidth, low latency, and one that handles scales. And you'll see pictures like this of what they call 5G slicing, of basically 3 separate networks running side by side, each of them delivering different kinds of services. Finally, I'll show you some of these. I don't know what to make out of this news that came out of Russia at some point. Basically, they're building their own internet. And it's not just for them. They want to get some other countries to use that internet. you know, to protect from outside influence, whatever that means. But basically, this is feasible today. That's what I'm trying to say. And if a country can do it, you know, certainly a company can do it. And we may see more and more of this for all sorts of reasons. These are political reasons. There is also, today is the day, June 11th is the day where net neutrality dies in the US because of the new rules. And so net neutrality figures a lot into this because that is something that's going to hasten the fragmentation because now the ISP now has no obligation to do any sharing, and it can completely slice its network in response to whatever the content providers are willing to pay and ask for. And this is from the New York Times. You can read it if you want in an editorial about net neutrality and how it's basically killing the internet. Of course, you're not killing networks, right? We will always have networks and digital content moving over networks. What they really mean is the internet as we know it today, a single infrastructure for everyone to use, is basically on its way to disappearing. Okay. So this is really the kind of my prediction in the future, and I hopefully showed you some evidence. So let's talk just briefly about so what. So okay, so it's happening. You know, what's the big deal? So the first thing I want to say is that I think we are ignoring it as a research community. Certainly, the funding agencies are not really talking about it explicitly. That the internet is fragmenting, and we should really think about networking research differently. In fact, there was a time when, at least in the National Science Foundation, I know there were some efforts here in Europe as well, were looking for this. They realized the internet was fragmenting, the cycle was not operating. They weren't really explicitly saying that, but we're not able to change things. So let's build a new network, design a new network, again, a single network from the ground up that will not ossify. And there were lots of attempts to do that. Unfortunately, none of them really succeeded to do that, basically design a new network that would not ossify. There's a lot of intellectual contributions from these projects, but we still have the old network with the old protocols and people working around it with all these bypass and new protocols. So I think still people are not willing to give up, okay, from this notion of a single network. But in my mind, you know, the fragmentation is a good thing for networking because it opens up the research agenda, and now we can each come up and say, well, here's a new way to build this new network to do this particular service or this particular set of meet this particular set of requirements. There is on the flip side, though, something that we have to be careful, that this one network did give us some things, right? So we have to watch out for that. One of them is that it gave us the economy of scale, but also gave us a low barrier to entry. Many of the services that are very successful today commercially really started out because they could deploy on a shared single network and go to a lot of customers without actually spending a lot of money to get started. Once they got started and became big businesses, they didn't care anymore. But I think not having a single network that everyone can use will stop, you know, small people from being able to big services that then will mushroom into big businesses. So the challenge, I think, for us is how do we maintain these features, the low barrier to entry, the economies of scale for some side of networking, and then you know, embrace the rest of this world that will allow us really more creativity and more imagination in how to build networks. So just to leave you with this, I think networking is not going away. The challenges, basically, we have a network that works, it has some issues. There are people responding by developing new ideas and just going off on their own with these separate networks. But the internet demands are not stopping. The scale is not going to end. The new services, sometimes it's hard to imagine, but I can see things that, you know, just based on history, that in 10 years we'll be doing things that we can't even imagine today in networks. Hopefully, ossification will stop talking about it, because then we will have these, you know, we would have really realized that really we will have many networks, so things cannot be ossified. There's some trends that I really completely didn't talk about here, but there's a lot of work on network programmability, which will make the many networks really not what it sounds like, which is completely brand new hardware and software for every single application. Really, we're going to take the hardware and software and reprogram it for different applications and use it. So it might give us some economies of scale, but still many networks, right? So this may be something to think about a little bit more than what I've brought up here. So let me remind you of the takeaways that basically I've argued that this iterative cycle is really fundamental, and keeping it going is really important to keep the network evolving. It's stuck today because we have a single network that's ossified, but there's really nothing fundamental about this single network. We should just give up on that and basically embrace this idea that we may need new separate networks to do different things. And this new world with many networks is actually a good thing for networking research, because it will allow us to expand our horizons and be more imaginative in how we do networking. So thank you very much.
Thank you very much for this interesting talk. We have time for questions. Are there any reflections or questions?
So you talked about clean slate.
Microphone.
Okay. Hi, Bengt Dahlgren from SIX.
You have to stand.
Yeah, I want to hear him, and then I okay.
Is this on? Do you hear me? Is it recording? Okay. So you mentioned clean slate research, but you sort of dismissed that as within the same paradigm as the one network. But isn't that really opening up for the many networks with new designs that will live in parallel?
I mean, I saw the question of whether the clean slate world was about many networks, or basically a single network. So actually, that's a very good question. You talk to the people that were doing the funding for it. You ask them what is your criteria for success for that clean slate work. One of the ways they were thinking about it was eventually whatever technology comes out of it is going to replace the current single network. There was, I think, a school of thought, and some people, I think, if you were being realistic, you would think that way, that it would just produce ideas that then maybe infuse the current infrastructure. So either way, either replace the current infrastructure or get ideas to change the current infrastructure. Both, I think, still thinking of a future that had a single infrastructure that was going to deliver all services and all digital content. I don't think the clean slate world was thinking about having each of these projects become a separate network that then would run side by side. So there's nothing to say that it couldn't have, but I think it was going to be hard to argue, I think, from a funding perspective, to say that we're building many networks and one for each thing at that time. Anyway, so that's kind of the way I saw it, but yeah.
Thank you for an interesting presentation. I've never thought about exactly the way you presented it. In one of your last slides, you had a kind of a 5G network with the slides.
Yeah.
And that was very interesting, because you can now say, in each slice I have my own network, and I can run my own protocols.
Yeah.
And so of course you still will need a common infrastructure. So do you believe in this vision which the telecom companies today produce?
So I mean, I was actually pointing to it as an example of the thinking of the fragmentation, right? That that people were thinking that. So let me back up. The way they're visualizing it, there will be a common infrastructure at some level,
Right.
and then they will virtualize things on top of them. But at some level, these networks are separate. They're designed for separate set of requirements. You can argue why 3, why not 10 requirements? And so I don't know that it was completely thought out. Exactly how many slices we need. Why 3? Why not 5? Why not 10? And as you know, it's not really a reality. I mean, this is still kind of on the drawing board. There are lots of lower layer 5G issues that people still have to resolve before we get this far. So I actually don't have any predictions. I don't really work in that area, so I don't really have any long-term predictions about whether that vision will succeed or not. But I was pointing at it to say that that in that vision, the world is many networks, at least 3. And they were realizing already at that point, I don't think they were saying it explicitly, but there is no way to have one network satisfy all the requirements, even from a technical point of view. So that's really what I was using it as evidence that this thinking about the fragmentation is already built into a lot of people's thinking. So.
Any final questions? Yes.
Thank you for the nice presentation. I have a problem about the end user's experience with this new trend. I mean, how do you think about, from an end user's perspective, if now this content provider build and manage their own networks, how will this new trend, how they will impact the end users?
Yeah.
Now I can access internet and I can find the information from different content provider and from all the network.
Yeah.
But if the network is splitted and managed by many companies and content providers, how it will be?
Yeah. So I can see the fragmentation happening in two directions. In one case, the user will be completely aware that they are using a separate network. There are examples. The Sigfox network is you have to have a separate interface, and you are completely aware that you are not using the internet. The spread network for the stock traders, again, they are completely aware they're going on this separate network. So whatever machine might have a connection into the big internet, but then they have a separate connection. There are examples. So I think for normal users accessing, the streaming services, the search services and so on, you will not be aware of it. You're not, for example, you're not today aware of the fact that Google is not using certain protocols, all hidden from you. And that is very valuable. I don't see the content providers ever kind of giving you a separate interface for different services. So they've been so far able to do it with the structure, basically by kind of creeping into your ISP and having separate arrangements with the ISP to kind of give you the illusion that you're using this shared infrastructure with the same interface. But very quickly, your traffic kind of gets split around within the ISP depending on what service you're using. And the fact that with net neutrality, the ISP still had to kind of give you equal share with other services. With net neutrality gone, the ISP now can even within its network completely have a separate slice or separate provisioning for certain services just because they pay more. So, but I think it's too valuable. The fact that you have a single interface is too valuable. But the question is what happens just after your interface. So you'll always, I think, have a single interface in most cases.
Thank you for your presentation. Actually, I wanted to ask that what does guarantee that the network fragments won't ossify? I mean, when the fragment increases, and I wanted to know.
Yeah, and network fragments will ossify. And the thing is, if you allow many networks, then if one ossifies, then you do a different one. You just build a different one altogether, right? You just stop using, or you keep using it for whatever it's stuck at, and then you can always build a new network to do something different.
So when we are speaking about fragmentation, we are fragmenting services, am I right? Or just...
No, I'm thinking that the actual network that you are using is also matched to the service, and that's a separate fragment from the rest of whatever you're using. Okay, it's not so things can ossify individually, but then you just use something else. Just use something else, or build something else. If it's not satisfying the requirements, then if your model allows you to have different networks for different things, then people will build a different network for something different. If the old network will still work for whatever it was designed for, and if you need to, and maybe even adaptable to new things, but at some point maybe it gets stuck. And now you need it for something else, you just build something on the side and use that.
So we create a new fragment for our new needs.
Right, exactly, yeah.
And
yeah.
So we can't change the previous service, or I mean, we can't change the...
If you cannot, so again, what I think will happen is some of these fragments will be able to adapt over time, but at some point, I think everything will get ossified over time. And then people will start building new things eventually. Okay.
So let's thank Mostafa again.
Thank you. Yeah, thank you.
We've also security.